All right, so Module 5 is on semiconductor junctions. Okay, semiconductor junctions, there's two types of junctions we're going to talk about. We're going to talk about PN junctions, when you put a P-type and an N-type material together, and then we'll also talk about metal semiconductor junctions. Both are important for different semiconductor devices. So here's some context. What we're going to be talking about. In the last module, what did we talk about? We said we've talked about N-type and P-type semiconductors in the previous section. We drew energy band diagrams for them. We understood the four mechanisms of carrier processes, four carrier processes of generation, recombination, drift, and diffusion. So in general, we were dealing with uniform materials. Everything's N-type, everything's P-type, everything's undoped. In this chapter, we start talking about what happens when you combine different types of semiconductors together. So a diode is basically a P-type and an N-type semiconductor put next to each other. Some of you remember this from Electronics 1. Okay, so this section is going to cover conceptually what happens if we put a P-type and an N-type semiconductor together. You basically get a diode. And you probably remember what this picture looks like from Electronics 1. You have the classic picture of a diode. So my pen isn't working properly. I need a new battery. Let's see. There we go. The classic picture of a PN junction looks something like this, or a diode. P-type material and an N-type material. So by now you know what a P-type and N-type material is. You put a voltage source across there, plus and minus. So this is basically a diode. Okay. So in your Electronics 1 course, you've talked about what the model is for a diode. You know that it has an exponential IV characteristic. It only conducts current in one direction. So in the negative end, the current goes something like this. And when you get to very large reverse biases, there's another phenomenon called reverse breakdown that causes the current to increase rapidly once you get to a large enough reverse voltage. How many of you remember these curves from Electronics 1? Okay, about half of you. So that's good. So this class is about semiconductor physics, so we're going to go into the physics of the diode and understand where this exponential characteristic comes from. In doing this, we're going to understand more about semiconductor physics, what carriers do, the electrons and holes, what they do. So there's going to be a physical interpretation of this device. We're going to talk about energy band diagrams. How do we draw energy band diagrams to understand diode behavior? And then we'll start to derive some of the equations. We'll derive the diode equation, actually. And then we'll start understanding some of the second-order effects, like reverse breakdown. So after we talk about PN junctions, standard diodes, we'll talk about metal semiconductor junctions as well. So this is sort of a preview. We're going to start off with PN junctions by talking about the physical interpretation, a diffusion and drift balance. So the picture looks something like this. We'll start talking about the depletion layer, the depletion region. Then this is physically what happens in the device. We're also going to understand how to interpret the device using energy band diagrams. And you've drawn energy band diagrams for P-type semiconductor. You've drawn energy band diagrams for an N-type material. When you put them together, the energy band diagram looks something like this. We'll get into the details of how you would go about drawing that diagram and how that diagram will change if you apply a voltage to the diode. So we'll talk about band bending, diffusion and drift of carriers, and also something called the built-in potential. Built-in potential is that you hear about diodes they act as a battery, 0.7 volts across it. That's what's called the built-in potential. So we'll talk about what that is. And then finally, the last part is going to just look at the diode as a circuit element. We'll try to understand what the capacitance is, what the steady state currents is, the exponential IV relationship, what happens when you apply reverse voltage to it, and some of the transient behavior of the diode. This will be the third part of the module. So let's start right off with the physical interpretation, because I think it's a nice lead-in from the previous module. Okay. Now, let's just do this thought exercise, though many of you may already know how this works already. So I want you to do this thought experiment. We put a p-type material and an n-type material next to each other. Okay. And somehow we've designed the thing so that the p-type material and n-type material are right in contact with one another. There's no air gap separating them. So the question is, what's going to happen here? And I want you to think about this question in terms of last module when we covered the 4 carrier processes: generation, drift, diffusion, recombination. So I want you to think about which one of those processes are going to happen in this situation. I told you that those 4 processes can be used to analyze any new device. So you've never seen this device before. Let's apply them. Okay, why will diffusion happen? Concentration gradient between the two. Right, that's correct. So we took the 4 carrier processes: generation, drift, diffusion, and recombination. All right, so we're looking at the 4 carrier processes, and as Raphael said, and Michael, you get diffusion. The diffusion arises from the fact that you have a concentration gradient. Where's the concentration gradient here? What's that? Between the whole thing, yes. So let's talk about specifically, if we're talking about holes, which one has a higher concentration of holes? Yeah. So the p-type material has a high concentration of holes. The n-type material has a very low concentration of holes. So the holes are going to diffuse from high to low concentration, right? So we've established that. That's the thing that drives it the most. So let's write down the fact that we have a bunch of holes here. Okay, and the holes are going to diffuse over to this side because the other side is at a lower concentration of holes. What's going to happen after the holes diffuse over to the n side? Recombination. That's correct. So we can write down X. That X means they're recombining. Now, I've drawn these arrows different lengths because remember from the last problem on Module 4, we found out that the holes will diffuse different amounts before they recombine. Right? This is kind of like a step concentration gradient. So the holes will diffuse over to the n side, but some holes will get further than others before they recombine. What is the average length a hole diffuses before it recombines? What is that called? We had a definition for it last time. It's close, not quite the carrier lifetime. It's related to the carrier lifetime. Diffusion length, right? The average distance that any of these holes recombine is called the diffusion length. Okay, I'm getting caught up in details right now, but the point I wanted to make here was that we've already established a couple things. We've looked at a new thing. We said, okay, well, there's diffusion because there's a concentration gradient. There's some recombination happening here. There's also generation. Remember, generation and recombination are always in balance. So if you have some recombination happening, there's also generation happening. But let's focus on the diffusion and recombination. To complete the story, we have electrons. The electrons are also doing the same thing. Remember, there's a high electron concentration on the n side. The electrons will then diffuse over to this side, and they will also recombine. So that's essentially what sets up a lot of the interesting physics in the p-n junction. Bonus question of the day, is there drift? Initially, no. Okay, but eventually there will be some drift, and the reasons for that are a little bit more complicated. We'll get to why that is on the slide. Okay, but it's good. We've already kind of gotten a sort of understanding of this. Let me just erase some of this extra junk here. Okay, so let's go back to this slide now. This is the physical interpretation of the p-n junction at equilibrium. The p-type semiconductor is right next to the n-type semiconductor. The holes are represented as white circles. The electrons are represented as blue circles. Can you imagine that the p-type semiconductor has a lot of holes, very few electrons. The n-type semiconductor has a lot of electrons, very few holes. You put the two materials together, you get diffusion. Diffusion from electrons from right to left, diffusion from holes from left to right. So the diffusion creates an imbalance of charge. Now let's talk about that. So we've covered this thing here. Now we'll talk more about this next class period. But one of the things that happens in a diode is that when these electrons diffuse over here, when the holes diffuse over to this side, they leave behind positively and negatively charged ions. Okay, and to get a picture of why that is, let's just jump ahead a little bit. Again, we'll come back to this later. Remember that a p-type material has these, it's doped with boron. It's doped with a column 3 element. So there's a boron ion here, and for every boron atom that you put in there, you create a hole. The boron has an effective -1 charge. The hole has an effective positive charge. Now we just mentioned that the holes diffuse from left to right. So when this hole leaves, it leaves behind a boron ion, which has an effective negative charge. All right, we'll come back to this, but I just want to illustrate it right now. Now, in the case of the n-type material, this one's actually easier to understand. N-type material is doped with a column 5 element. So in arsenic, for example, arsenic has one extra proton than all the, its atomic number, it's a column 5 element, so it has one extra proton compared to silicon. It also comes with one extra electron. So it donates this extra electron to the lattice, and this electron is free to move. When this free electron moves, when it diffuses over to the left side, it leaves behind this positively charged arsenic ion. Everybody with me here so far? Okay. The difference between an electron, a movable charge, electrons and holes are movable. Okay, they can diffuse, they can drift, and so on. But these charges here are immobile. This arsenic atom is actually bound to the silicon atoms around it by a covalent bond. Similarly, this boron nucleus is bound to the other silicon atoms with covalent bonds. So the electrons and holes can move, they can diffuse, but these charges cannot. So that's why you end up, when the electrons and holes diffuse, electrons diffusing this way, holes diffusing the other way, they leave behind these positively and negatively charged ions. So you leave behind positively charged ions on the N side and negatively charged ions on the P side of the device. So this region where a lot of diffusion is happening, where the electrons have left and the holes have left, this is called the depletion region. It's called the depletion region because it is depleted of mobile carriers. It's depleted of electrons and holes. What's left behind is just these positively charged ions and negatively charged ions. So if you have a bunch of positive charge and you have a bunch of negative charge, what kind of electric field does that generate? If you line up a bunch of positive and negative charges next to each other. And think back to your capacitor. Okay, I think my phone. Think back to your capacitor problem in physics, where you have you put a voltage across two plates of a capacitor, and you build up positive charge on this side, and you build up negative charge on this side. So the electric field points from positive to negative, right? You draw an electric field like this. It points from positive to negative. So in this case here, we have a bunch of positive charges here, a bunch of negative charges here. So this sets up an electric field that points from right to left. All right. Now that we have an electric field, that means we're going to have drift current. Okay, so we go these four processes we mentioned here. Diffusion happens initially. After the diffusion, you form the depletion region. That results in an electric field pointed from right to left. And so this will ultimately set up drift current. So the drift current will cause the holes to go this way. So due to drift, due to the electric field, the holes drift this way, and the electrons drift this way. All right, so the holes are diffusing from left to right, but due to the electric field that was set up, they drift from right to left. The electrons diffuse from right to left, but then they drift from left to right. Okay, we'll talk more about that in next class period when we come back to this. Okay, so let's stop here and we'll start. I'll pass out the quiz. All right, so quick review then. So what happens when we put a p-type and an n-type material next to each other together? Okay, the first thing that happens, we had the four carrier processes. You should think about like what happens in the basis of those four processes: generation, drift, diffusion, recombination. So you said the first thing that's obvious that would happen is that you have a gradient of carriers. You have a high electron concentration on this side, low electron concentration here. So electrons diffuse from high to low concentration. They diffuse to the left. Similarly, the holes diffuse towards the right. When they do that, they leave behind what's called the depletion region. All right, this diagram schematically shows what's happening. Remember that a column 5 element, this is what the lattice may look like. It's mostly silicon atoms, but there are some areas, some atoms where the silicon has been replaced with arsenic at column 5. Okay, that arsenic has a higher atomic number, so it comes with one extra electron, one extra proton in the nucleus. When the electron diffuses over to the p side of the junction, as I just mentioned, it leaves behind a positively charged ion. Okay, so this red circle that you see in this, thank you, the red circle that you see in this chart here represents this arsenic ion. All right, so the electrons diffuse over this way, leaving behind this immobile charge. Now the difference between this charge, a positively charged arsenic ion versus a positively charged hole, is that the hole can move. It's a mobile charge. This is an immobile charge. Electrons can move too. The electrons and holes are mobile. So similarly on this side, you have a boron ion which has a net -1 charge. When the hole diffuses over, it leaves this net -1 charge here. That's this black circle here. So, as a result of this is where we sort of left off last time. Whenever you have a series of positive charges and negative charges next to each other like this, that is very similar to a capacitor. Right? If we just look back at our definition of a capacitor is just when we put voltage across two parallel plates. There's a metal plate here, a metal plate here, and a dielectric material in the middle. You build up positive charge on one plate, and you build up negative charge on the other plate. Right? And you have an electric field that points from the positive charge towards the negative charge. Similarly, in this region, we build up an electric field that points from the positive charges, the red circles, to the negative charges, the black circles. So this electric field is pointed from right to left. So what's going to happen as a result of that electric field? Which way are the electrons going to go? Which way? They'll move towards the right. That's correct. They move opposite the electric field. Right? So the electrons are diffusing from right to left, but they're drifting from left to right. Okay. Similarly, the holes are diffusing from left to right, and they drift from right to left. Holes drift in the same direction as the electric field. Okay, that's sort of where we left off last time. Now, what we're going to start off with today is the idea that these two are balanced. The drift currents and the diffusion currents are balanced at equilibrium. They sum up to 0. Okay. Now, if you think about this, this has to be true. If you just took a p-type material and an n-type material together, if the net current was not equal to 0, then you'd have like an infinite source of energy, right? So you do have some diffusion currents, you do have some drift currents, but they balance each other out at equilibrium. All right, that's summarized by this formula here. So this Jn diffusion plus Jn drift is equal to 0. Jp diffusion plus Jp drift is equal to 0. All right, and why don't we just fill in these arrows here? What's the direction of, let's start with Jn drift. Yeah, let's think about this for a second. Now, in this, I'm asking specifically for the direction of the current. I'm asking for the direction of Jn. Jn drift. It won't be towards the right. It'll actually be towards the left. Because remember, the electrons are drifting from left to right, but we define current as the movement of positive charge. The flux, you're correct about the flux. The flux is opposite the electric field, but the current is always in the same direction as the electric field. When we're talking about drift currents, remember, the drift currents are always in the same direction as the electric field. The flux of the electrons are opposite, but the current is the same direction. So, there we go. So the drift currents are always in the same direction as the electric field. So this one here is Jn drift, this is Jp drift. Okay, and the diffusion currents, the electrons are diffusing from right to left. So what is the direction of the diffusion current? So electrons are diffusing this way. What direction is the current? Yeah, it's the opposite, right? Left to right.
Diffusion happens in the same direction as the potential difference, right?
Diffusion happens from high to low concentration. Yeah, exactly. And the holes are diffusing from left to right. So the diffusion current is in the same direction as the holes. It goes this way. So in terms of signs, Jn diffusion is positive. JP diffusion is positive because it's oriented from left to right. JN drift and JP drift are both negative because they're oriented from right to left. Any questions so far? Okay. All right, this is the more on the depletion region. We talked about this already. Again, I want to differentiate between the fact that electrons and holes are mobile ions and the arsenic and boron nuclei with the charges are immobile ions. The reason I'm emphasizing that is because if you want to create an electric field, the charges must be immobile. So in other words, they have to be static. Okay, you have to have static charges here, static charges here. That's what will allow you to create an electric field. Right, so like many things in nature, it consists of two processes which are sort of, they oppose each other and they balance each other out. So this phenomena really is how the PN junction gets a lot of its properties. The fact that you have this depletion region here is the reason why a diode has that 0.7 volt potential across it. It's the reason why a diode has an exponential IV characteristic. It's the reason why a diode is a nonlinear circuit element, whereas a resistor and other things are linear circuit elements. Okay? All the unique properties are just coming from the fact that you have this depletion region. We'll come back to more about the depletion region later. Let's talk about the energy band diagram now. So let's start off with something that we remember first. Right? We know how to draw the energy band diagram for a p-type semiconductor. We know how to draw the energy band diagram for an n-type semiconductor. So this is what the two band diagrams look before the two materials are placed in contact with one another. For the p-type material, you have the Fermi level located down here. For the n-type material, you have the Fermi level located up here. So we should all be comfortable with drawing the band diagrams, and you should also be able to, if I were to ask you to draw this on a test, you should also be able to tell me what the specific location of the Fermi level is, meaning how far it is from EI, how far it is from EC, or EV. So when you put the two materials together, when you put that p-type and the n-type material together, what happens is that the Fermi levels form, they come together, and they form a continuous Fermi level. Okay. And at equilibrium, no discontinuity or slope can appear in the Fermi level. The reason behind this is the statistics of what the Fermi level means. Fermi level is telling us that, you know, it's that 50% mark. When you're at the Fermi level, the probability of finding an electron is 50%. The probability that an energy state is occupied by an electron is 50%. And as the farther you go above it, that probability drops to 0. And as you go below it, the probability increases to 100%. That was the definition of the Fermi level. It had to do with Fermi-Dirac statistics. And another part of Fermi-Dirac statistics would state that if you're at equilibrium, no discontinuity or slope can appear in that Fermi level. This probability of finding an electron, when you put the two materials together, the probability of finding an electron at a certain energy state is the same in this area, the same in this area. What happens instead is that the bands bend around the Fermi level. Okay, so if you could imagine taking this guy and lining up the Fermi levels, okay, if you were to line up EF and EF here, the band diagram would look something like this, and then you connect EC together and you connect EV together. All right, we'll be doing an example of drawing this band diagram. Okay, this results in a phenomenon called band bending. Right, so if we try to understand a little bit of the intuition behind this. The Fermi level represents that 50% level, okay? So that Fermi level must remain constant through the material. But on one side we have a p-type semiconductor, another side we have an n-type semiconductor. And each one of the sides of these semiconductors, it has different properties. There's a forbidden range of energy states up here for the p-type semiconductor. There's a forbidden range of energy states here for the n-type semiconductor. Now, the next leap of faith that we took is we said that the bands have to be connected. EC here must be connected to EC here. EV here must be connected to EV here. Okay. Now, the way that you can, if it helps you to understand, to think about it this way, remember that there are a whole bunch of energy states above EC. Okay, so this whole region that I'm highlighting with the hand here, this is all filled with various numbers of energy states. There's a whole bunch of energy states above EC here. Okay, so when you have all the energy states on one side and all the energy states on the other side, this creates an area in the middle here where the energy states an electron can transition from one energy state here to a lower energy state here. Holes similarly can transition from energy states here to energy states up here. Okay, so this becomes a continuous band that sort of dips down like this. These are all energy states up here. And similarly over here, they are also energy states. A band of energy states. Okay? So in terms of like a rule of thumb, some of these rules that you see here, you can just write those rules down, and by the end of the semester, you will have a whole list of rules for analyzing and interpreting energy band diagrams. We're just introducing one of them right now. Okay, no slope in the Fermi level, and then I guess this is also a concept that you have a phenomena called band bending. Okay, so this slide shows how to draw the energy band diagram. The first thing you would do is draw the p-type semiconductor. So start with EC, EI, and EV. First you draw EF. Okay, so EF will be a flat line at equilibrium. Starting with the p-type semiconductor, just like the problem you've done in your previous exams, if you know what the doping of the p-type semiconductor is, you can find the location of the Fermi level. So you draw the Fermi level in there based on that. So you do a calculation, EI minus EF is equal to KT ln of Na over Ni. You find the location of the Fermi level here. And then you continue that Fermi level all the way across to the N side. Then you draw the N-type material on the right. So what you would do is, the Fermi level is already positioned here. All you're doing here is adding the EC, EV, and EI here based on the location of this Fermi level. So you already know how to calculate the distance between EF and EI based on the doping on the N side. And that's how you'd be drawing the location of the three bands here. Okay, and the last step is you do the band bending. You connect the three together like this. Okay, so you have these separated, and then you just connect the bands like this. Now, this region here, the region that has this bent band, where there's a slope in the band, where the slope is non-zero, this is the depletion region. Okay, another rule of thumb that you can write down or jot down is that wherever there's a slope in the band diagram, that's where you have an electric field. Okay, so for an electron, electrons would prefer to go to lower energy states. Okay, so an electron that's up here would sort of find an energy state here, would find another energy state here, and so on. And in doing so, the electrons would actually move down the slope like this. The movement of the electron down the slope is referred to as drift current. Similarly, if you have an electron here, electron sees a lower energy states. The electron will, occupy lower energy states like this, and it'll move down here. Now, what this means in the valence band, we're not really concerned with electrons because most of the band is full. What we are concerned with is the empty states, the holes. So a hole, interestingly, a hole will actually move up the slope, okay? Because as electrons move down the slope, if there's a hole here, for example, let me draw this out. So let's say there's a hole here. So if there's a hole is an empty state, so that means an electron would prefer to occupy this empty state. Okay? So as a result of this electron going down, the hole is going to move up. I'm getting ahead of myself on the slides here. We'll get to this in a second. So holes will actually end up moving up the slope as a result of this continued event of electrons occupying the hole. The hole will actually move up to higher and higher energy states. Electrons move to lower energy states, holes move to higher energy states. Because electrons always like to occupy the lowest energy state. So a hole moving up the slope is referred to as drift current for holes. Okay, so I apologize for the confusion. Okay, we finished up this slide here. Now, let me just delete this. There. So this slide is about analyzing the energy band diagram. Just want to get rid of this. Okay. So the electric field rule, the slope of the band diagram is proportional to the electric field. So from this diagram, if you were to see these red lines here, if I were to draw an energy band diagram like that, if I asked you which direction is the electric field pointing, what direction would the electric field be pointing?
Right to left?
Right to left. Why is it right to left?
Because the electrons are moving to lower energy levels, so they're going the other way. And
Right.
The field goes opposite the electron.
That's correct. That's correct. Electrons are going this way, so they're going opposite the field. So the electric field's pointing from right to left. Just a quick rule of thumb way that you can remember it is that the electric field is proportional to the slope. Excuse me. So there's a negative slope here, right? It's going from high to low as you go from left to right. Negative slope means the electric field has a negative value, negative polarity. Negative polarity means the electric field is moving from right to left. Positive polarity means it's moving from left to right. The second part of this, analyzing this energy band diagram, if I were to draw this energy band diagram for you and ask you to figure out what the doping is on the N and the P sides, you should be able to do that. Because you know what the, if you know what the distance is between EF and EV is, or if you know the position of the Fermi level on this side relative to the other bands, and you know the position of the Fermi level relative to the other bands on this side, then you can figure out the both the whole the doping concentration on the P side and the doping concentration on the N side. A lot of the properties of the diode, most of the properties of the diode are determined by just the doping on the P side and the doping on the N side. And we'll talk more about that as we go. So just a qualitative rule of thumb, the closer EF is to EV, the higher the hole concentration. All right, so the smaller this gap, the higher the hole concentration on the P side of the junction. And then on this side, the closer EF is to EC, the more the electron concentration on the N side. So I've drawn these as a triangle, meaning what I've done here is I'm showing the electron concentration as a function of energy. Remember the energy band diagram, the y-axis is energy, right? And the x-axis in this case is the spatial coordinate. It's a spatial position. On the n side of the junction, I'm drawing the electrons. I'm using an n-type material. There are many more electrons than holes. We're more interested in what the n-type, the electrons are doing at this moment. We're more interested in knowing what the holes are doing here at the moment. Why have I drawn a larger concentration of electrons here and a lower concentration of electrons up here? Say that again?
As we go further than the EC,
Uh-huh.
for the n-type, will be lower the electron concentration.
Yes, that's correct. The electron concentration will be lower the farther we go up from EC. Remember, think back to the chapter where we discussed Fermi levels. The higher you go up from the Fermi level, the lower the probability of finding an electron. So there's going to be a high concentration of electrons at this energy, but the farther we go up, the lower the electron concentration will be. So that's why I've drawn this as a triangular stack. Lower concentration up here, higher concentration down here.
It also has to do with the fact that, like you just said about 2-3 minutes ago, like electrons want to occupy the lowest energy level.
Electrons like to occupy the lowest energy state.
The higher you go, the less electron, the less likely you are going to find an electron because it wants to occupy the lowest state.
Absolutely right. Yeah, the higher in energy state you go, the less probability of finding an electron because electrons like to occupy the lowest energy state. Good. Now, the converse is true for holes. There's a high hole concentration here, and as we go lower in energy, there's lower hole concentration. This is also has to do with the Fermi function. Okay, it's sort of the opposite of this. You know, but it's based on the same idea. At higher concentration, at higher energy states, less likely to find an electron. Okay, so at higher energy states, there's less probability of finding an electron, so a larger probability of finding a hole. Okay, remember the probability of finding a hole is 1 minus the probability of finding an electron. So that's why this triangle is inverted compared to this one. So we have this stack here representing the electron concentration. We have this stack here representing the hole concentration. Now we want to understand diffusion current. Diffusion current goes from high concentration to low concentration. All right, so you can see that there's a high concentration of electrons on this side. There's a very low concentration of electrons on this side because the Fermi level is so far away from EC. In a p-type material, because of that, you have a very low electron concentration. So electrons are going to diffuse from right to left. Just drawing in those arrows here. So what happens when an electron diffuses from right to left? You can see that these electrons will run into a barrier. Okay, that barrier is represented by this line here. Now what that physically means is it's an energy barrier. All right, the energy states are all up above EC. Okay, in this area that I'm sort of shading with my arrow here. The electrons here will get to this point, and remember, electrons don't like to go to a higher energy state. They prefer to stay at a current energy state or go to a lower energy state. So these electrons, when they get to this point, they're trying to diffuse from high concentration to low concentration, but only some of the electrons end up diffusing over like this, because only a small portion of the electrons have enough energy where they can diffuse over here and not be impeded by this potential barrier. Similarly for holes, the holes diffuse this way. They see a potential barrier too. Holes will prefer to go to higher energy states. Electrons will prefer to go to lower energy states. Holes prefer to go to higher energy states. So when the hole diffuses this way, it doesn't see any energy states up this way, so that's a potential barrier here. So a small fraction of the holes diffuse over to the N side. Okay, so that's shown here like this. Now, there's also drift current. So electrons like to drift down the slope, as I just mentioned, higher energy states to lower energy states, and holes will drift up the slope. So the holes go this way, the electrons go this way. You can't see okay, you can see the arrow there. So what this diagram is expressing now is expressing you have some diffusion current, diffusion of electrons this way, diffusion of holes this way. Some of these carriers run into the potential barrier. That potential barrier, that potential, that slope, is also driving some drift current. The electrons are drifting this way, holes are drifting the opposite way. So these processes that we talked about, this is sort of the physical model of what the carriers are doing. Now we see sort of an energy band model for what is happening. Okay, so I want you to understand these processes in terms of the physical model as well as the energy band model. Any questions so far? Okay, I think that when I first studied this, I think the most confusing part for me was this idea that holes go up the slope, electrons go down the slope. Okay, the electrons going down the slope sort of makes sense because electrons like to occupy the lowest energy state. So if there are a whole bunch of energy states here, you can imagine the electron hopping to this energy state, then to this energy state. It sees a slightly lower energy state here next to it. So just by hopping energy states, it goes to, it gradually goes to lower and lower energy states. But the hole moving up the energy state is the same thing as an electron going down the energy state. Okay, so just remember that. And the last thing I want to emphasize is that these are drift currents shown in green. The diffusion currents are shown in red. Yes?
The what's called the energy barrier. Is that why diodes are kind of like a one-way street when it comes to the current flow?
Yes. So the question was, this energy barrier, is that one of the reasons why diodes only conduct current in one direction? The answer is yes. The details of that we'll be getting into in the next lecture or two. But yes, that allows current flow in only one direction. Yep.
These few holes or electrons that make it through, is that analogous to what leakage current is in the physical?
That's another good question. So the small number of electrons and holes that are able to drift, is that what causes leakage current? The saturation current that you see? Yes, that's true.
Oh.
Some of these drift currents are responsible for that saturation current. But again, it'll make more sense once we derive the diode equation. Yeah. This potential barrier turns out to be very important. The electric field that you build up. So just to make sure that we relate the concepts together, this depletion region that forms generates an electric field. Okay, that electric field is what is shown here in the band diagram. The fact that you have a slope in the band diagram here means you have an electric field. And as we'll find out, the distance, the amount of bending here actually correlates to the built-in potential. So that's this last point here. The energy barrier determines the built-in potential V0. The distance here in electron volts, so how much bending we have here in electron volts, tells you what the built-in potential will be in volts. So for a typical diode that has a built-in potential of like 0.6 or 0.7 electron volts, the distance, the amount of bending in the energy band diagram will also be 0.6 or 0.7 electron volts. Okay. Yeah, so this distance here is Q times V0. V0 is a built-in potential in volts, so 0.6, you can imagine 0.6 or 0.7 volts. You multiply that by Q, and you'll get 0.6 electron volts. And electron volts is a unit of energy. And that's the energy difference between EC on the P side and EC on the N side.
Is it going to be same? This level and that level?
You mean this
Yes.
level and this level?
Yeah.
Yes. Yeah. Yeah, and Nasser brought up a good point here. The question was, is this distance and this distance going to be the same? Is the potential barrier going to be the same on both the EC and the EV side of things? And the answer is yes. Because EC and EV, the distance between EC and EV does not change. Okay, that's the band gap, 1.12 electron volts for silicon. The distance between EC and EV is a fundamental property of silicon. If it's silicon on this side and it's silicon on this side, then EC and EV are pretty much, the distance between them are pretty much fixed. So you can imagine that these are lines that are running parallel to one another. All these lines are running parallel to one another. Yes?
But what if you change the silicon to Germany?
Yes. So what happens if you change the material from one type to the other? Let's say the P-type material is silicon, the N-type material is germanium. Yes, then the distance will change. And that will affect what the band diagram looks like. The way that you can draw these band diagrams, the rule will still be the same. If you start off with the P side of the junction, draw the Fermi level, extend that Fermi level all the way across to the N side, and just draw the band diagram of the N side around it. And you'll see that the bands will bend slightly differently if you have two dissimilar materials together next to each other.
If you change if you junction different material, then the speed of drift and diffusion is different for the electrons and holes, right?
That's correct. It will change. Well, you can never get, even if you put two dissimilar materials together, you still can't generate current out of it. The drift and diffusion currents will always balance at equilibrium, even if you have two dissimilar materials. But the band diagram will look slightly different. You might have an electric field that looks slightly different on one side. The slope of the band diagrams will look different. Yeah, and we can try an example of that if you're interested. So you're talking about heterojunctions where you have two dissimilar materials and create a junction out of them. For the purposes of this class, we're mainly going to be talking about just p-n junctions made in one type of material. Okay, later we'll talk about metal semiconductor junctions, but that's a different topic. So calculating the built-in potential. There are two ways to calculate the built-in potential. One is through a formula, and the other one is through just the energy band diagram. I want you to be able to do both. The built-in potential is an important quantity in determining the electrical performance of a diode. The built-in potential, again, is that the potential required to run current through the diode. Let me just remind you from circuits, the symbol for a diode is something like this. So this is a diode symbol here. In order to push current through the diode, the voltage that you put across the diode has to be greater than V0, the built-in potential of the diode. If you remember this from circuits 1, when you're operating diode, you usually have to put a voltage greater than about like 0.6 or 0.7 volts in order to get current to go through the diode. And once you go above 0.6 or 0.7 volts, the current shoots way up. So you put a voltage across there. If you measure the current, you'll have pretty small currents right up to the point where you get to where the built-in potential is. And then the current will shoot way up. So this built-in potential it's important to be able to find it. And what you can do now is just by drawing the energy band diagram, if you know the doping on the P side, you know the doping on the N side, you can draw the energy band diagram for the diode, and from there you can directly calculate the built-in potential. Because remember that when you draw the band diagram, the distance, the amount of bending here between EC here and EC on this side, this is the built-in potential. This is equal to Q times V0, where V0 is the built-in potential. Okay, we can also derive the built-in potential mathematically, assuming that a step junction of P and N-type material with some doping density. That's what's shown on this slide. So I would like us to try it both ways. Let me first go over this slide, and then we'll do an example problem. So a formulaic approach to calculating the built-in potential is to assume that you have a step junction. So a step junction means you have a certain amount of concentration on this side, and you have a certain amount of concentration on this side. Let me rephrase that. A certain doping density on the left side, a certain doping density on the right side. And that doping density changes immediately as we go from P-type to N-type material. There's not a gradual change in doping. Okay, if you assume a step junction, you can do this analysis. The other assumption you make is that the diffusion and hole currents are zero at equilibrium. So you start off with this relation JP drift plus JP diffusion is equal to 0. The drift and diffusion currents are balanced. From the previous module, we have a formula. Let me zoom in here so it's a little bit easier for you to see. We're going to go through this step by step. The formula for drift current is Q times U times P, P of X times E of X. This was the formula for drift current from the last module. And this is the formula for diffusion current from the last module. The sum of the two is equal to 0. All right, so, excuse me. So the next part here, you just do a mathematical manipulation, and you get mu p over d times the electric field is 1 over p times the concentration gradient. All right, so that part was relatively straightforward, just arising from this basic relation here. The next thing you do is you use the Einstein relationship. Does anyone remember what the Einstein relationship is? How do you remember it? D over mu equals KT over Q. So using the Einstein relation, this D over mu over here becomes KT over Q. And you also use the definition of voltage. The electric field is the derivative of voltage. E is equal to dV dx, if you remember this from electromagnetics. And you arrive to this, you simplify this E of x to dV dx. Now you have a derivative on the left side, a derivative on the right side. You can integrate both sides of the equation. So on the left side, you're taking the integral with respect to the voltage. On the right side, you're taking the integral with respect to the concentration. You have to be careful about the limits. So what you're doing is you're taking the integral from one side of the junction to the other side of the junction. So as you go from one side of the junction to the other, this VP is going to go to Vn. So the voltage on the P side and the voltage on the N side. So you're integrating from the left side of the PN junction to the right side. Here, you're also integrating from the left to the right side of the junction, except this integration is done in terms of concentration. So this is the whole concentration on the left side of the junction. This is the whole concentration on the right side of the junction. So even though you've learned this principle in mathematics that whatever you do to one side of the equation, you have to do to the other side of the equation. Well, one thing you can do with integration is, you can integrate both sides of the equation, but it's okay to integrate the different sides with respect to different variables. You can integrate this side with respect to V. You can integrate the right side with respect to P, so long as the limits of integration are done appropriately. It's just a little mathematical trick that, if you don't know already, might be interesting. So after we get this integral, we can simplify the two equations. You get two logarithmic functions here, and you get just a linear function here. When you simplify, you get this relationship here. V0 is equal to KT over Q, ln of Pn divided by Pp. P sub n is a whole concentration on the N side. P sub P is a whole concentration on the P side of the junction. You can use NP equals Ni squared, our friend. Simplify this. And ultimately, you will arrive at this equation here. V0 is equal to KT over Q, ln of Na NT over Ni squared. Okay, so this is the formula for finding the built-in potential. What I would like everyone to do is I would like you to derive this formula using an energy band diagram. It's a good exercise to do. It helps us understand. So yeah.
Are we ever going to be asked to derive it like you did on that slide?
No, I won't ask you to derive. I won't ask you to derive it this way. Okay. However, I would like you to try to derive this formula without going through this proof. I would like you to derive this formula just by drawing the energy band diagram, and actually you should be able to arrive at the same formula. Okay, so let me be specific here. So let's say we have a PN junction that looks like this. Oh. So this is the P side of the junction, this is the N side of the junction. Okay, well, we can do some of this together. So the P side of the junction has a doping Na, and the N side of the junction has a doping Nd. Let's erase this from here. This is what the energy band diagram looks like. You have EC here, EV, and then EI. What I'd like you to find out is how do we find this distance here? So you have everything you need to know. So I would like you to derive, this formula is equal to, this is Q times V0. And what I'd like you to find is what is V0 in this setup. So just try this out. I'm sorry? Not by using the formula I just showed you on the previous slide. I would like you to walk through this. I would like you to walk through this problem by first finding the distance find a formula for the distance here, find a formula for the distance here, and then see if you can find a formula for the distance here. Okay, so find A, find B, and then these should be easy. Finding A and B should be easy to do, and then see if you can find what this distance is, C. We'll call this C. So take a minute and we can try that. So this distance A, how can we find that distance A? Okay. EI minus EF on the P side of the junction. So let's just give this a subscript P. And what is the formula for that? KT. It's just KT, actually. Yeah, KT ln NA over NI. Okay, good. Similarly, B, this is equal to EF minus EI on the N side of the junction, and this is equal to KT ln of ND over NI, right? Okay, so now what is C? What's the formula for C, the distance there?
It will just be
A plus C, plus C.
going to be EC minus
Getting close or close.
EC minus F minus EF.
Put on your geometry hats and see if you can figure out how do you figure out C in terms of A and B?
C, A plus B.
Yeah, that's it. That's it. You know, I know my drawing's terrible, so, you know, if I were to really draw these lines in parallel, you'd see that C is equal to A plus B. Because these are three parallel lines, right? So, in other words, if I can state that another way, however much bending you have in EI, so A plus B, right? A plus B will be this distance here, right? It's the amount of bending in EI. Because the three lines run parallel to each other, the amount of bending in EC is the same as the amount of bending in EI. Is the same amount of the bending as in EV. All right, so this distance C is going to be equal to A plus B. So this is going to be KT ln, so just do KT of ln NA over NI plus ln of ND over NI. So what happens when we sum up the two natural log functions? You multiply the contents together, right? So you end up getting KT ln of NA ND over NI squared. All right, now V0, well, the distance C is equal to Q times V0. So V0 is equal to C divided by Q. So V0 is equal to V0 equals C divided by Q. So this is KT over Q ln of NA ND over NI squared. Alright, so this is our derived formula of V0 just based on the energy band diagram. Okay, so you can see that this formula matches up with the formula that we derived using more of a physical model. This formula was derived using the physical model, and the one we just derived was using the energy band model. The two worlds actually, they match up. You know, they're two ways of describing the same things. What you'll find is that your intuition for certain things, the energy band diagram will make sense. For certain things, the physical model will make more sense. And but I expect you to be able to understand both. Okay, so let's do an example problem. And while we're doing this example problem, if anyone finishes early and would like to just take a bathroom break, we can do our break sort of integrated with this example here. So we have in the example problem, we have a step p-n junction. The doping on the p side of the junction is 10 to the 18th. The doping, yes.
When are we doing presentations today? Sorry.
Yeah, the presentations we'll do. Excuse me. We can do those right after we do this example problem. So after break. How many folks are doing the presentations today? Okay. All right, great. So we'll have time. Yeah, so let me continue here real quick. So the example problem, we have a step p-n junctions with Na equals 10 to the 18th. So the doping on the p side is 10 to the 18th. The doping on the n side, Nd, is 5 times 10 to the 15th. So what we want to do is calculate V0 using an energy band diagram to find the built-in potential. First, calculate the Fermi levels of the p and the n regions, draw the band diagram, and then use that band diagram to find the built-in potential V0. The second way of doing it is just to use the formula that we just derived, given on the last slide. And when you compare the results, the two results should be the same. So it's a good way of checking over your answer. Okay, so I'd like you to try that just to get used to doing these types of problems. And if you're done with it, just you can take a break. We'll start again in about 7 to 10 minutes. And just gonna. All right, so let's just do this one together real quick, just so you have the answer. I'm not going to do both parts of it just in the interest of time. Let's just find out what the built-in potential is. KT over Q ln. So this is the formula here. Ln of Na Nd over Ni squared. So KT over Q is 0.026 at room temperature. Ln, you have 10 to the 18th. Okay, and then your Nd is 5 times 10 to the 15th over Ni squared, 1.5 times 10 to the power of 10 squared. All right, so what do we get for this? 0.8. 0.8 volts. Okay, a couple of things I want to point out. 0.026, this is the KT over Q is equal to 0.026 volts. So the units for this is volts. The units here and here is 1 over centimeter cubed. Right? The units here is 1 over centimeter cubed. So the units do cancel out. And you're left with the volts as the final unit. All right, so regardless of how, whichever way you calculate it, the built-in potential should be 0.8 volts. Okay. So you can see that the voltage, that built-in potential of a p-n junction is basically determined just by the doping on the two sides of the junction. And we can control that. Okay, it turns out if you use smaller doping, lower doping will give you a smaller built-in potential. A larger doping will give you a larger built-in potential. Okay, so let's stop here for a second so that we can do the presentations. Okay, so let's talk about space charge region now. So we're going to zoom in now and talk specifically about the depletion region. What kind of, what are the electrostatics and what are the electrical properties of this depletion region? Okay. It turns out that depletion region, as I mentioned, is responsible for many of the properties of the diode. Why it has this nonlinear IV characteristic, why it conducts current in one direction, and so on. A few facts. Okay, remember the depletion region was formed when electrons diffused this way and the holes diffused this way, leaving behind these positively charged ions on the n side of the junction and negatively charged ions on the p side of the junction. So as we have seen, carriers are constantly moving through the depletion region due to diffusion and drift currents. So electrons are diffusing this way, holes diffusing this way. Due to the electric field built up by the depletion region, there's also drift currents, so holes are drifting this way, electrons are drifting that way. And we said that the drift and diffusion currents are balanced. At any given time, there are very few carriers in the depletion region. Okay, the reason why is because you have this very strong electric field. Okay, carriers are, they're diffusing. They kind of exist in this region, electrons and holes. You have electrons and holes in this region too. But in the depletion region, one of the reasons why it's called the depletion region is because it's depleted of mobile carriers. It's depleted of electrons. It's depleted of holes. When you build up an electric field here, going back to this picture here, if we have a very strong electric field, what's going to happen if we put a hole here? If we put a positively charged carrier, what's going to happen to that thing? Yeah, it'll get accelerated. It'll get accelerated down this way, right? So whenever mobile charges are placed in an electric field, they get accelerated. They get swept away. Okay, so even if you were to have an electron or hole in this region where there's a strong electric field, it wouldn't stay there very long because it would get swept out. So that's what this depletion approximation is that it's saying that there aren't any mobile electrons or holes in this depletion region. The charge density in the depletion region is due only to donor and acceptor ions. It's due to the immobile ions, the positive ions here, negative ions here. There are very few electrons and holes in that depletion region. We assume that there's none, essentially. And that's the reason why it's called the depletion region. So there's a bunch of concepts that we can talk about. Some of these concepts will be related to circuits. Some of them will be related to electromagnetics. But it's important to understand these to understand the physics of the depletion region. So the depletion region, as I mentioned, is similar to a capacitor, a region of positive charge next to a region of negative charge. Now, whenever you have a capacitor, there's this rule of space charge equality. Electromagnetics tells us that the number of positive charges must equal the number of negative charges. In the capacitor relationship, some of you may recall this formula here. The charge on a capacitor Q is equal to the capacitance times the voltage. Q equals CV. So have any of you seen this formula before from physics, okay, or electronics, electromagnetics? Q is the number of charges. C is the capacitance, and V is the voltage. The voltage is the voltage put across the capacitor. C is the capacitance of of the capacitor given in farads. This is in volts. And Q is the amount of charge. It's given in coulombs. Okay, this Q can be the number of positive charges on this side of the plate, or it could be the number of negative charges on this side of the plate. The two are equal to each other. The number of positive charges is equal to the number of negative charges. So in the depletion region, this is also true. So if we were to add up the number of positive charges on this side, and you were to, it would be equal to the number of negative charges on the other side. So in terms of the junction, what those charges are. Remember that a positive charge is this arsenic ion. A negative charge is this boron ion. So the number of arsenic ions in the depletion region is going to be equal to the number of boron ions in the depletion region on the P side. Okay, coming back in here. So as a result of this, the difference in doping results in different widths of the two regions. Okay, now suppose in this particular example, the N side had a larger doping than the P side. So there's a larger concentration of the arsenic ions on the N side. Okay, the doping concentration is larger here than it is here. Okay, so by the concentration we mean like that the density of these dopant atoms. So if it has a higher doping density, that means there's a smaller spacing between the atoms, between those donor ions. Sorry. So yeah, in this example, the N side had a higher doping, the P side had a lower doping. There's a larger space between the dopant atoms on the P side. So what ends up happening is that the P side has a larger depletion width than the N side. Okay, that's sort of intuitively what's going on. Now, if you want to express this like mathematically, you can express it mathematically as well. You can look at the charge density. So the charge density on the N side of the junction is Q times ND plus. Okay, let me redraw this here so we can. So rho of X, the rho is charge density. What's the units for charge density? Coulombs per cubic centimeter would be the volumetric charge density. Right, and if you want to do area charge density, then it would be coulombs per centimeter squared. So if we plot charge density on this axis, so we have the PN junction here like this. This is the P side of the junction, this is the N side of the junction. Let's say the depletion region starts here like this. Okay. The charge density would look something like this. All right, because remember you have positive charges on the N side, and then you have negative charges on the P side. The doping density is higher on the N side, so the positive charges are spaced closer together. The spacing is larger on the P side of the junction. Now remember, the number of charges on this side has to equal the number of charges on this side. So as a result, the width of the junction on the N side is smaller than the width of the junction on the P side. So we can call this X sub N. This is the width of the junction on the N side. And X sub P is the width of the junction on the P side. Now the charge density is equal to Q times NA. All right, what's the units for Q? Coulombs. NA? 1 over centimeter cubed. Okay, so we're talking about volumetric charge density. Okay, I put the area density just to be complete, but we're talking here about volumetric charge density. Okay, I'm sorry. I put Q. This should be QND. Sorry. Okay, so the total charge in here is the area under the curve. So if we do Q, the area here is Q plus, the area here is Q minus. So Q plus is equal to Q times ND times X sub N. Right. Now, the units here is coulombs. The units here is 1 over centimeters cubed, and the units here is centimeters. So this gives a total of coulombs per centimeter squared. Okay. Now this isn't giving the total charge. In order to get the total charge, we also have to multiply by the area of the diode. All right. This is one small detail that you have to, that if you don't understand, it may confuse you. Remember, a diode is actually a three-dimensional object, right? So you have a p-type material and an n-type material. Right? The interface between them is where all the interesting stuff happens. Right? So this area here, the area that separates the p and the n-type material, that is the area of the diode. So to get the total charge, you also have to multiply by the area, which has the units of centimeters squared. And this will give you coulombs as the unit. Okay, this last part of charge equality will just take a few more minutes. So let's just bear with me here. Q minus, the charge density here is Q times NA. Remember, these are negative charges. Okay, the total charge on the left side of the junction is the area under the curve. If you integrate charge density, you get charge. So Q minus is equal to Q times NA times XP. And then remember, we also have to multiply this by the area, A. And getting to the charge equality, what we're saying is that the Q plus has to equal Q minus. The number of positive charges has to equal the number of negative charges. So just do the math real quick here. A times X sub N, ND times Q is equal to A times X sub P times NA times Q. A lot of these cancel out. Areas cancel. Q cancels. And you're left with this nice formula, X sub N times ND equals X sub P times NA. This formula is very useful because it tells us, as an engineer, what can we control? We can control the doping. We can control ND and we can control NA. So if we solve this formula, ND over NA, you get XP over X sub N. Right? So we can control the ratio of X sub P and X sub N just by controlling the doping. Right? Now X sub P and X sub N, the dimensions of the depletion region are very small. They're like less than tens of micrometers. Okay, but we can control what the dimensions of the depletion region are just by however much we dope the N side and the P side. Okay, and the physics of this works out very nicely. Okay. I know we did go over this relatively quickly, but you can always look over this stuff on the video if you'd like. So just as this last example here, suppose the P region has twice the doping of the N region. The difference in the widths of the two regions is also going to differ by a factor of 2. Whichever side has, if one side has twice the doping, the size of the depletion region on that will be 1/2. Right? So it's an inverse relation. Higher doping, smaller depletion width. Okay, we'll end with that today. I'll see you all Tuesday. Keep in mind we may have a quiz on Tuesday, so make sure that you prepared the last part of chapter 4.
Yeah.